the concept of equally likely outcomes. Hello, everyone. Welcome to today's lesson. Before we dive into the complex calculations of probability, we need to start with the very basics. As you can see on our first slide, when we study probability, we aren't just jumping straight into plugging numbers into formulas to predict how likely an event is to happen. That would be a mistake. Before we can use any mathematical formulas, we must first take a step back and truly understand the nature of the outcomes of our experiment. We need to know what kind of results we are actually looking at. This brings us to a very important point. The foundation of what we call theoretical probability rests entirely on one specific, crucial condition. We have to start with the assumption that our outcomes are equally likely. Over the next few slides, we are going to break down exactly what that means and, more importantly, how to identify when this condition is and isn't met. Understanding equally likely outcomes. First, let's look at the terminology. In any random experiment, whether you are flipping a coin or picking a card, there are several possible results that could happen. In mathematics, we refer to these individual results as outcomes. So, when do we use the term equally likely? We say that two or more outcomes are equally likely if none of them has a higher chance of occurring than the others. In other words, no single result is being favored over another. To make this even clearer, think about it. This means in terms of repetition. If you were to perform the same experiment many times, say 1,000 times, each equally likely outcome should appear approximately the same number of times. You wouldn't see one result popping up significantly more often than the rest. Finally, for this to hold true, there must be no physical or mathematical bias. This means there is nothing about the setup, the weight of the object, or the method of the experiment that pushes the result toward one specific outcome. Now that we've established that the foundation of theoretical probability relies on the assumption of equally likely outcomes, let's dive deeper into what that actually means in practice. In the next slide, I'll show you some concrete examples, like using a fair coin or a die, to illustrate this lack of bias in action. Examples of equally likely outcomes. Now that we have defined what it means for outcomes to be equally likely, let's look at some concrete examples to see this concept in action. To make things easier when we talk about these experiments, we often use the terms fair or unbiased. When you see these words, you can immediately assume that the object we are using, whether it's a coin, a die, or a spinner, is perfectly balanced, meaning there is no hidden trick or weight shifting the results. Let's start with example A, tossing a fair coin. When we toss what we call a fair coin, we are assuming that the coin isn't weighted or rigged toward one side. Let's break this down step by step. First, we identify our possible outcomes. The coin can only land on either heads, which will denote as H, or tails, which will denote as T. Next, we analyze the bias. Because we've stated the coin is fair, there is no physical reason why the coin would prefer landing on heads over tails. Therefore, our conclusion is that the outcomes H and T are equally likely. Moving on to example B, let's look at rolling a fair die. A standard 6-sided die is that familiar cube with faces numbered from 1 to 6. Let's apply our step-by-step analysis here as well. First, we identify the possible outcomes, which are the set of numbers 1, 2, 3, 4, 5, and 6. Next, we look for bias. In an unbiased die, the weight is distributed perfectly evenly across the entire cube, so no specific number is heavier or more likely to appear than any other. Consequently, we can conclude that each of these 6 outcomes is equally likely. This means the chance of rolling a 1 is exactly the same as the chance of rolling a 6. As we move to the next slide, we will look at what happens when these conditions are not met, and how the presence of bias or different quantities can change the probability entirely. Contrasting with non-equally likely outcomes. Now, up until this point, we have been focusing on fair scenarios, like the coin toss and the die roll we just discussed, where every result has the same chance. However, it is crucial to realize that not every experiment results in equally likely outcomes. In many real-world situations, the conditions of the experiment actually favor one specific result over another. When this happens, we say that the outcomes are not equally likely. To make this distinction clear, let's look at a different kind of example, drawing a ball from a bag. Imagine you have a bag containing 5 balls in total. 3 of them are red and 2 are blue. You reach into the bag and draw one ball at random. Let's perform a step-by-step analysis to see if the outcomes are equal. First, let's identify our possible outcomes. In this experiment, the result can only be either red or blue. Next, we need to analyze the quantity of each. We can see that there are more red balls, specifically 3 red balls, compared to only 2 blue balls. Now, let's evaluate the likelihood. Because there is a higher quantity of red balls in the bag, you naturally have a higher chance of picking a red ball than you do of picking a blue ball. Therefore, we reach our conclusion. Because the chance of picking red is greater than the chance of picking blue, these two outcomes are not equally likely. As we move to the next slide, we will summarize these key concepts and look at some common pitfalls to avoid when identifying these probabilities. Key takeaways. First, let's revisit our core definition. Outcomes are considered equally likely only if no single result has a higher chance of occurring than any other. If one result is even slightly more probable than the rest, we can no longer call them equally likely. Second, keep an eye out for the terms fair or unbiased. As we saw with our examples of the coin and the die, these are the specific words mathematicians use to describe tools that are perfectly balanced, ensuring that every possible outcome has the exact same chance of happening. Third, and this is a very important point for your future lessons, this concept is a prerequisite for the classical formula of probability. You can only use that standard formula, where you divide the number of successful outcomes by the total number of outcomes, if you have first confirmed that all the outcomes in your experiment are, in fact, equally likely. Finally, remember the influence of quantity. As we saw in our example with the red and blue balls, when you are selecting items from a group, the number of items of each type is what determines the likelihood. Even if the outcomes, red and blue, are the only 2 possibilities, the fact that there were more red balls than blue balls meant they were not equally likely. All right, let's bring everything together with our key takeaways from today's lesson. Now, before we wrap up, I want to highlight a few common pitfalls that students often encounter, so pay close attention to the next slide. Common mistakes. First, be very careful about assuming that all outcomes are always equal just because there are only a few of them. A common error is to think that if there are only 2 possible results, for example, winning or losing a game, then they must be equally likely. But as we discussed with the bag of balls earlier, the number of outcomes doesn't dictate their likelihood. In a game, the probability of winning depends heavily on the rules, the player's skill, or even the equipment used. Just because an outcome is one of the few possibilities doesn't mean it has an equal chance of happening. Second, try not to confuse the concept of an outcome being possible with it being equally likely. This is a subtle but crucial distinction. Think back to our example from slide 4, where we had a bag with 3 red balls and 2 blue balls. It is certainly possible to draw a blue ball, but because there are fewer blue balls than red ones, drawing a blue ball is less likely than drawing a red one. Always ask yourself, is there a bias or a difference in quantity that favors one result over another? Now, before we wrap up our lesson, I want to touch on some common pitfalls. Even students who understand the basic definitions can sometimes fall into certain traps when solving probability problems. Let's look at slide 6, which highlights 2 major mistakes to avoid. If you can keep these 2 distinctions in mind, you'll have a much stronger foundation for the more complex probability formulas we will be studying in our next lesson.